All right. Good afternoon, everybody. Let's get started. All right. Welcome to L04. So in last lecture, Arvin started describing how we could implement circuits using BlueSpec, how to use the BlueSpec hardware description language to implement some basic arithmetic circuits. And in particular, we took a glimpse at how to perform binary addition. So today, we're going to dive deeper into binary arithmetic. First, we're going to see how to encode negative numbers in a way that makes addition and subtraction very simple and very natural. We're also going to see how to do binary multiplication. And then in the second part of the lecture, we'll start, we'll see different design approaches for adder circuits. And so adders are used all over the place. Not only that, they are also very good at introducing different design strategies that you'll use over and over again in your digital circuits. OK, so as a reminder, this is the same as last lecture. So if you have an n-bit string, right, you can use it to encode up to 2 to the n possibilities. And you can assign a different number to each of those 2 to the n possibilities, right? And the way we do this is starting left or starting right to left. We assign increasing powers of 2 to its position, right? And then we encode a number by essentially multiplying the value at its position by its own weight, right? And so last time we saw that if you take this number here, right, it's the same binary string. What value does this encode? Well, you can start going digit by digit. So it's 0 times 2 to the power of 11, 1 times 2 to the 10, 1 times 2 to the 9, and so on. And so if you keep going, you'll get essentially that this is 2000. Can anybody tell me how to do the opposite operation? So what if I have a decimal number and I want to translate it to binary? Yes? Yes. So you subtract the largest power of 2 until you get 0, right? So this is very easy. So suppose that you have 11. This is not 3. It's 11. So what is the largest power of 2 that's smaller than 11? 8. And what do you get? 3. 3 minus 2 is 1, and 1 minus 1 is 0. And so what you get is that 11 is 2 to the power of 3 plus 2 to the power of 1 plus 2 to the power of 0. And so it is 1, 0, 1, 1, right? OK. Any questions? All right. So as we saw last time, the smallest number that you can encode is 0. The largest number, 2 to the n minus 1. So strings of bits are essentially what the machine manipulates. But for us, they're tedious to write, to manipulate. It's very easy to make mistakes. So for our convenience, we often use a higher radix notation. We use a base that's larger than 2, than binary. And if you choose a base that's a power of 2, then it's very easy to transcribe from that base to binary and vice versa, because it's essentially a grouping, an ungrouping of binary digits. And so the most popular encoding in this is hexadecimal, or base 16. So basically, with hex, we use numbers 0 through 9 to represent the first 10 digits. But then, of course, we ran out of decimal numbers, so we use letters A through F. This table, by force of sheer practice, you'll end up learning it by heart. So even if you're doing in other courses, you'll tend to see hex over and over again. OK, and so given this, this number that we had before, well, it's a 12-bit number, so that's 3 4-bit groups. And so we can take each group of 4 bits, starting from the smallest place, and translate it, again, using this table, right? So this would be 0D7, right? And so this binary number, this 12-bit string, we can write as a 3-digit number. And we encode the base by saying 0x. Sometimes you'll see 0h to denote that is hex. OK, so we saw how to do binary addition last time. But not only is binary addition the same as in decimal, but also binary subtraction is the same. So let's, again, go through the process of how to do binary addition. So you have 14 plus 7. What do you expect in base 10? 21. But how do you do this? You do 4 plus 7. You go digit by digit. So 4 plus 7 is 11. And so we carry 1. We call this a carry. And then we do 1 plus 1, 2. Right? So binary, same thing. We saw this last lecture. You encode the numbers in binary. You add them digit by digit. 0 plus 1, 1. 1 plus 1, 0, and we carry 1. 1 plus 1 plus 1, 1, and we carry 1. 1 plus 1, 0, and we carry 1. And we get 1, 0, 1, 0, 1, which is 16 plus 4 plus 1, 21. Subtraction is the same thing. So now, we want to do 14 minus 7. How do we do this? In decimal. So back to grade school. So you also go digit by digit, and then what do? I hear borrow. Yes. So 7 is larger than 4, so we, instead of doing 4 minus 7, we do 14 minus 7, which is 7, and we borrow 1. So this is the same way that this is called a carry. This is called a borrow, right? And then minus 1, or 1 minus 1 is 0. So we get what we expect. Binary, same thing. 0 minus 1, we don't know. Right? So 1, 0 minus 1, 1, and we borrow, or 1. Same deal. Right? 1 minus 1 minus 1, 1, and we borrow 1. 1 minus 1 minus 1, 1, and we borrow 1. 1 minus 1, 0. Right? Is this clear? OK. So we get 1, 1, 1, 7, as expected. What about this? So what is this? What are we trying to do here? What are these numbers in decimal? 0, 1, 1, 1, 0, 1. Yes, 3 minus 5. What do you expect in decimal? Minus 2. OK, so let's use our usual procedure. So 1 minus 1, 0. 1 minus 0, 1. 0 1 minus 1. 0 minus 1 is 0, and we have to borrow 1. And now what? What do I do with this minus 1? Yes? Sorry? So I could keep going, right? I would get basically 1s all over the place, right? But I would always have this minus 1 to borrow. Or sorry, here, this minus 1 to borrow. So I would get an infinite string of 1s if I kept going, with zeros, right? So what does this minus 1 mean? I mean, what is this saying? Why can't we just do something and represent the number that we want to represent? Yes? Yes. And have I told you how to represent negative numbers? No. So, of course, it's out of range. Right? But basically what this means is minus 2 to the power of 3 plus this positive number over here. Right? So this is -8 plus 6 minus 2. Yeah, it makes sense. But we need a way to encode negative numbers. And so that's what we're going to do in the next few slides. But before we do that, I want to talk a little bit about what we call binary modular arithmetic. And so in general, you want to use a fixed number of bits to perform operations. And so if you use a fixed number of bits, addition and basically all other operations, so subtraction, multiplication, are going to generate some extra bits that are going to be out of your range for some input values. And so, you know, this, when you get bits out of the range that you can represent, this is called an overflow. You're essentially going out of range. And the common approach to handle overflow is to just throw out these extra bits. So for example, with addition, you can get an extra bit, an overflow. This is what we call an overflow bit. And if we just ignore it, this is essentially the same as what we call modular arithmetic. So this is the same as following each operation by modulo of 2 to the power of n, where n is the number of bits that you can represent, right? And so modular arithmetic has a lot of very nice properties. Basically, visually, you can see it as numbers wrapping around. And so addition would be going clockwise in this wheel. And then subtraction would be going counterclockwise, right? So for example, if you want to do 1 plus 2, so you go 2 positions this way, you get 3. If you want to do 6 minus 2, you do 6, 5, 4, right? This is fairly, it's a very natural way to think about what's going on. And so going back to our example, what we're getting is, if we try to do 3 minus 5 modulo 8, what do you get? So you start from 3, you go back 5 positions, and you get 6, right? What we just saw. OK, any questions? If you get this, you've gotten most of the lecture. Yes? Is it a problem? No, but it's going to actually help us quite a lot. So you have to understand modular arithmetic because we'll do everything, or we'll actually derive an encoding for negative numbers that makes operations very easy by leveraging modular arithmetic.
I have a question.
Oh, yes?
How do you know to set it to like what mod to set it to?
Because if you have 3 bits, then that's equivalent to doing modulo 2 to the power of 3. So it's the number of bits that determines the modulus. OK, so as I said, we're missing a way to encode negative numbers. Let's start with the most natural approach, right? With base 10, with decimal, which is what we use every day, we use what we call a sign magnitude representation. So we represent the magnitude in using decimal digits. And then we put either a plus or a minus sign before the number to denote whether it's positive or negative, right? And so the first thing that we can try is to use the same approach for binary numbers. So we have what we call a sign bit here. We use 0 to denote that the number is positive, 1 to denote that the number is negative, and then we just have the magnitude. So in this case, this number would be minus 2,000, right? This was the same bit string as we saw in the first slide. OK, what issues does this have? This is actually not very good. There are some problems. Yes?
You can't necessarily distinguish from like the next bit up.
Sorry?
So you might not be able to distinguish from the next bit up.
So that is a general problem, that if I give you a number and I don't tell you whether it's encoded as an unsigned or a signed number, if this digit is 1, you really don't know. And that is going to be a problem of every representation. You have to know whether it is signed or unsigned. Yes? Yes, that is a really nasty problem. So what happens if you want to, for example, compare 2 numbers for equality? Well, so with unsigned numbers, you just have to go digit by digit, see that they're all equal, and that's it. But now you have to have special cases for, well, if this is 0, then don't count the sign bit because you have plus 0 minus 0. But even worse, there's more problems with this, right? So because we're having this this sign bit essentially as something completely independent from the magnitude, this makes the circuits for addition and subtraction more complex. Essentially, you end up needing to do several special cases to handle the sign bit. And you need different circuits for addition and subtraction. OK, so we had a good thing going with unsigned arithmetic, because we saw that unsigned arithmetic essentially had a one-to-one correspondence with modular arithmetic. Can we find an encoding for negative numbers that retains the nice properties of modular arithmetic? Yes? Sorry? You're jumping too far ahead, yes. But if you were to relabel individual digits here, or individual numbers, what would you do? What would you change? OK, so we make 7 minus 1, 6 minus 2. Right? And it all makes sense, because 0 minus 1, well, we'd end up in minus 1. Right? Minus 1 minus 1, minus 2. So we're doing exactly the same operations. Right? So we keep going, and we keep going until minus 4. Why minus 4? I mean, in principle, you could stop anywhere, right? Why don't I use this encoding where I stop at minus 3 and then 4 stays positive? Yes?
Yes, because 0 would be considered as a positive, so then you would have equal amount of positive.
So you can consider that 0 is positive, and then you have, it's nicely split across this half. Yes?
It's kind of convenient that all the negative ones have 1.
Exactly. Exactly. So it's really nice that the most significant bit still denotes whether the number is negative, right? And this actually maps to the actual formula for deriving the decimal representation. What this means is that we take the previous formula for positive integers, right? Which before this went from 0 to n minus 1, but instead we take the most significant bit and give it a negative weight, right? So in an n-bit string, the weights are going to be from 2 to the 0 to 2 to the n minus 2, and then minus 2 to the n minus 1, right? OK, any questions?
It seems like we just before said that having a sign bit at the very beginning was dangerous.
Yes.
How is this not dangerous?
It is different because you don't have. So if you go back, this in sign magnitude representation was minus 0, right? And this is minus 1, right? Now we've made it minus 3. So even though you can still interpret it as a sign bit, the construction is different. There's not a one-to-one correspondence, right? We're changing how we represent the negative numbers. But that's a good question. OK, so what is the most negative number? What is the most negative number that you can represent with this in general, with n bits? Yes, exactly. Right, so the weight of the most significant bit. The most positive number is the largest number, so 0 followed by all 1s, right? And that is 2 to the n minus 1 minus 1. And what does the all 1 string represent? What number does it encode? Negative 1. OK. So what's really nice about 2's complement is that it makes arithmetic really, really easy. So as you mentioned a couple of slides ago, if you want to negate a number, so if given a, you want to compute minus a, all you have to do is invert all the bits and add 1 to the resulting number. And you might be wondering, well, why is this? And to show this, we actually have to do a very short proof. So this works because of the following reason. You can say that minus a plus a equals 0, which equals minus 1 plus 1, right? And if you reassociate terms to get minus a on the left side, then you get minus a equals minus 1 minus a plus 1. OK, so let's take a look at minus 1 minus a. Minus 1 minus a is the all ones string, right? The all ones bit string, and then the bits of a, right? And so what do you get? 1 minus a0 is, if a0 is 1, what do you get? You get 1 minus 1, which is 0. If a0 is 0, what do you get? 1. So you get not a0. And there's never any borrow going on here, because you're either doing 1 minus 0 or 1 minus 1. So this is essentially subtracting a from minus 1 is equivalent to negating all the bits. And then you add 1, and you get minus a. Right? OK, any questions? Yes? Oh, sure. So OK, let's go back. This just is a standard reassociation of terms, right? So this equality is simply just saying minus a plus a is 0, minus 1 plus 1 is 0, and you're just reassociating the terms to get to this equation, right? And now the key thing is, if you do this subtraction, just like we saw before, right? So you take minus 1, right, is the all ones bit string. And so if you go bit by bit, 1 minus a0, if a0 is 1, is 0. And if a0 is 0, is 1. So you're getting not a0. Is that clear?
A is the binary number?
Yes, it's a binary digit. So at this point, this is just a Boolean formula, right? So 1 x 1 minus x, right? If x is 0, then you get 1, and if x is 1, you get 0. That's an inverter. That's just not, right? And there's never any borrow, because you're never going over your 1, right? It's all ones. OK, so the nice thing about this is that you can perform subtraction, right, by just reversing the number or inverting the number and doing addition. And the good thing about this is that you don't need different circuits for addition and subtraction, right? You just need to first compute, given, if you want to do a minus b, you first compute minus b with this simple operation, and then you add a plus minus b. OK, so let's see a couple of examples of this addition or subtraction by addition at work. So first, let's try to compute 3 minus 6 using 4-bit 2's complement addition. So how do you represent 3 in 4-bit 2's complement addition? It's 0, 0, 1, 1, right? 6, 0, 1, 1, 0. And then how do we get minus 6? We invert all the bits and add 1. So we do 1, 0, 0, 1 plus 1, 1, 0, 1, 0. Right? OK, so let's do this. 0, 0, 1, 1 plus 1, 0, 1, 0. 1 plus 0? 1. 1 plus 1? 0, and we carry 1. 1 plus 0 plus 0, 1. 0 plus 1, 1. What is this number? It's a... So how do you translate this? I mean, you could go and reverse it again. So 0, 0, 1, 0 plus 1 is 0, 0, 1, 1. So it's minus 3. Right? And 3 minus 6 is minus 3. Good. So this actually works. Is this clear? Yes. Sorry, can you speak louder? How do you go from 1, 1, 0, 1 to minus 3? So if you go 1, 1, 0, 1, you invert all the bits. 0, 0, 1, 0. You add 1. 0, 0, 1, 1. Right. So anytime you get a negative number, you can, again, get the magnitude by doing the same process again.
Why did we add 1 in both cases instead of adding 1 for negation and subtracting 1 for the other way?
You add 1 every time that you want to negate a number. The only reason I am adding 1 to this result is just to show that it is minus 3. Okay, any questions? So if you're performing the operation, the only thing you have to do is add a 1 to get to the minus 6. Okay, so let's do something a little bit more interesting. 3 minus 2 using 3-bit 2's complement addition. So 3 in 3-bit 2's complement addition, still 0, 1, 1, 2, 0, 1, 0, minus 2. Can anybody tell me what minus 2 is? 1, 1, 0, right? Because 1, 0, 1 plus 1, 1, 1, 0. Okay, so if you add this up, you get 1 plus 0, 1. 1 plus 1, 0 and we carry 1. 1 plus 1, 0 and we carry 1. And 1. Okay, what do we expect 3 minus 2 to be? 1. And what did we get? Sorry? Out of range, yes. So if you keep the last 3 bits, it's just 1, right? It's what we want. But, you know, why do you keep the last 3 bits? You know, I'll just throw this one because it's bothering me. There's a meaning of this one, right? This one has a certain meaning. What this one means is that if we go back to our modular arithmetic wheel, right? You're starting from 3, and you are taking 2, turning it into minus 2, which is 1, 1, 0, and then going minus 2 or 1, 1, 0, 6 positions over, right? And so what this means, what this 1 means, is that you just crossed over 0, and that's fine. Right? Here, it's not happening because you are not getting, you're staying somewhere in the negative side, and you're not getting to cross 0. Okay, any questions? Good, so just one more operation, multiplication. So remember how in grade school, to do multiplication, you basically did this long multiplication method where you take the multiplicand, the multiplier, and then you went digit by digit, and you had to multiply the entire number by each digit, and then add things up 1 digit over. So you ended up with many additions. Do you remember how painful it was to get to remember all the multiplication tables because you had 10 times 10 possibilities, right? So my favorite thing about binary arithmetic is that what is A times B? Anybody? If A and B are 0, A times B is 0. A is 0, B is 1. 0. 1 times 0? 0. 1 times 1? 1. All right. Here's your binary multiplication table. Right? Cool. So with this, because it's so simple, binary multiplication is just repeated addition. And so the only thing that we need to do is go position by position, just like you did with long multiplication in grade school. But then you either, if the digit is 1, essentially add this number, or if the digit of the multiplier is 0, you add 0, or you do nothing. Right? So at each step, you're either going to add 1, 1, 0, 1, or 0. Right? So you start 0, 0, 0, 0, plus 1, 1, 0, 1, 1, 1, 0, 1, and then we add an extra. We have a carry of 0 here, and we go to the next digit, which is 1. So we add 1, 1, 0, 1 again, but it's shifted by 1 position, just like in the decimal case. So you keep going. In this case, this digit is 0, so we add 0, 0, 0, 0, and we get this longer number. And the last bit is 1, so we add 1, 1, 0, 1, and we get this end result, which is 143, which is 11 times 13, right? OK, any questions? Yes? Great question. No, there's a small difference. So you'll see this in lab 3. OK, so for the last part of the lecture, we're going to shift gears and talk about performance, talk about cost. Start worrying about how good are the circuits that you're designing. So far, we focused on functionality, right? How do we do these operations? How do we do addition? How do we do subtraction? Let's start thinking about how to do these operations efficiently. And so the one thing that I want to convey is that hardware design and software programming or software design are no different in this respect, right? So you have many possible ways to implement each particular function. Each particular implementation will have some delay, some area will consume some power. You typically care about some combination of all of those. And you need to use the right algorithms in your design to hit the right trade-offs. And so in general, if you think about the problem of designing a digital circuit, as you start with some description of the problem, and then you, the hardware designer, goes and turns this into a high-level description of a circuit that solves the problem, then you're going to go and use a synthesis tool, like we discussed in lecture 2, that gives you an optimized implementation of your circuit, maps it to the gates that we have in our standard cell library, and so on. And so because this says optimize, you might be lured into thinking that, hey, this is doing optimization. I don't really need to be that smart in producing a circuit description. As it turns out, you need to use the right algorithms here, or the tool is not going to be able to fix a bad implementation. Right? So for the most part, tools cannot compensate for an inefficient algorithm. And this is exactly the same as programming. You substitute hardware designer by programmer. You substitute high-level circuit description by program reading a high-level language, synthesis tool by a compiler, and then optimized circuit implementation by an optimized binary program. You have exactly the same issue. The compiler is not going to go and, if you're doing a quadratic time sort, it's not going to go and turn it into a n log n sort. And so this happens for basically all circuits that you're going to design. You're going to see different trade-offs, but we're going to study how to build a better adder by looking at different designs and see what different trade-offs we have in terms of delay and area. OK, so if we take a look at the performance of the ripple carry adder, we see that it's a simple design. It's essentially what we saw. It maps perfectly to what we've seen so far in terms of how do you do addition digit by digit. But it's kind of slow. And so the worst case path here can be triggered in several ways. But one possible example is, suppose that you start with all the bits of A being 0, and then all the bits of all the bits of A being 1, and then all the bits of B being 0. And the carry in here is also 0. And then you flip B0 from 0 to 1. So initially, all the carries are 0, and then what you get is this flip causes this carry to go from 0 to 1, which causes this carry to go from 0 to 1, which causes this carry to go from 0 to 1. And essentially what you have is a chain of propagation delays of each full adder, right? So you can derive the exact description of, or the exact propagation delay of the circuit by looking at the worst case paths between all the inputs and outputs. If the largest delay that you get is between seeing carry in and carry out here, then you'll have n times 1, n minus 1 times the propagation delay from carry in to carry out. And then you have to, for the last bit, cross an XOR gate from carry in to the sum bit to produce the sum bit. And so you can look at different adder implementations, and you'll get particular numbers. But the key problem here is this n minus 1 term, right? By changing the design of the adder, of the full adder, you could affect these terms. But you are going to have this long chain. And so we say that this propagation delay is order of n, which we represent by this theta of n notation here. And what this means is that the latency of the adder grows linearly with the width of the inputs, with the number of bits of the inputs that we want to add. Is this good? Are you happy with having linear delay? We can do better. Okay, so just as an aside, you might not have seen this theta of n or order n notation. This is actually used very frequently. So we say that g of n is theta or equals theta of f of n. That is, if g of n is of order of f of n, if and only if we can find two positive constants, c2 and c1, that when multiplied by f of n will both give an upper bound to g of n and a lower bound to g of n, except for a small number of integers. So you can have, for example, some integers. For small integers, this bound might not hold. But as n grows, this should be always larger, and this should be always smaller. OK, and so you might have seen also O of n, or big O notation. Big O, when we say that g of n is big O of f of n, it means only this first inequality, only the upper bound. Theta of n implies both inequalities. And so if I give you n squared plus 2n plus 3, we say that this is order n squared, right? Is of order n squared. Why? Well, because you can choose, for example, constant 2 here, right? 2 times n squared is always larger, or it's almost always larger than n squared plus 2n plus 3, and that itself is always larger than n squared for positive integers n. So in practice, what this means is that given this equation, you take the most rapidly growing term, you throw out all the constants, and that's your theta of n. That's your f of n. OK? Any questions? So we're interested in this asymptotic analysis because it tells us a lot about the performance of the adder for large numbers, for a large number of bits, without diving in too much into the constant factors. That said, the constant factors do matter. So when we're comparing particular styles of adders, if they're both log n, we'll see that we'll start getting different numbers because of the constants. OK, so let's try to build a faster adder in a very simple way. And so what I'm going to say is, look, your carry can be 0 or 1. So why don't we chop up the adder at its midpoint? And essentially, if we want to do if we want to add 32-bit numbers, what we're going to do is have a single adder for the low half of the addition, for the low 16 bits. And then we're going to have 2 adders for the upper 16 bits. And each of these adders is going to, one of the adders is going to take a carry in of 0, The other one is going to take a carry in of 1. Right? So we essentially compute both what the result would be with both options. And now the carry out of the low half selects which version of the high half addition we use. What have we achieved with this? What is the propagation delay of this circuit? Yes? Sorry? N/2, if you build this with ripple carry adders, right, this adder is going to be quite, the propagation delay is going to be quite long because you still have a linear chain here, right? But in general is the propagation delay of this adder plus the propagation delay of this max, because this adder and these two adders are going to take the same amount of time. And so, as you said, if we used 16-bit ripple carry adders on to implement each of these, we roughly divide delay by 2. That's great. But we can actually do better by applying the same strategy recursively. So what if I take this 16-bit adder and make it a carry select adder with 8 bits, an 8-bit high half and an 8-bit low half, and I take those 8-bit adders and make them 4 bits and so on. So in that case, what happens is that at each level, we're reducing the delay of the adder by a factor of 2, right? And we're adding 1 max delay. And that means that we get, what asymptotic behavior do we get? I hear logarithmic, and we get logarithmic because, again, a doubling adds a constant, right? A doubling in the number of bits adds a constant amount of extra delay. Okay, are there some issues with this adder? Is there something that, might not be so good? Yes?
It would take up more area.
You take much more area, right? Because now you have 3 adders, where in fact before we had 2. And also, and this is something that's not so obvious, but you'll see in lab 2, the delay of this max is not really constant, but it grows with log n. So it's adding a non-trivial extra factor. And you'll see exactly why this happens in lab 2, where you'll actually use a synthesis tool. Okay, so what most processors implement in practice is what we call a carry look-ahead adder. And so the idea of a carry look-ahead adder is to directly compute all carry bits in logarithmic delay. So you take your full adders, and instead of having this chain of carry in to carry out to carry in, carry out to carry in, we're going to have some extra carry generation logic that's going to take all the inputs, all the A's and B's and the C's, generate all the carries directly, and then feed them to the full adders. Now, the key idea here is to transform the chain of carry computations into a tree. And you might be wondering how you can do this, because if I give you something like an AND, right, a chain of AND gates or a chain of OR gates, do you know how to turn it into a tree? How to turn that chain into a tree? If I give you 32 AND 2 gates all in a chain, how do you build a tree out of that? Yes?
Connect the output of an AND to the input of another AND.
That's already how the chain is formed, right? So the output of one AND goes to the input of another AND, and then you have a long chain of propagation delay, right? So the propagation delay is the sum of all the propagation delays. Yes?
You can just connect the consecutive ones and keep on doing that, so you AND each consecutive one.
Exactly. So you can reassociate terms, right? So instead of having a chain, because AND, OR, XOR, and so on are associative operations, you can reassociate how you do the terms, and so essentially you can collapse the chain into a tree with much lower delay. But you cannot just go and reconnect full adders all over the place, right? Carries are not associative. And so to get this chain to tree behavior, we have to do some transformation on the equation that gives us the carry out given the carry in. So this is the original equation for a 1-bit full adder, right? So the carry out is 1 if either A and B are 1, or if A or B are 1 and the carry in is also 1. Right? And so you can rewrite this likely by calling G A times B, the generate, and P, A or B, the propagate. We can rewrite this equation as G or P and C in. So intuitively, what is this saying? What this is saying, and this is why these signals are called generate and propagate, is that if G is 1, then no matter what C in is, our carry out is going to be 1. And we say that this full adder is generating a carry. It's generating a carry out. And then if P is 1 and G is 0, then we're essentially propagating the carry into the carry out. So the full adder is propagating the carry. That's why these G and P are called generate and propagate. And so the key nice property of expressing the equation this way is that generate and propagate signals compose hierarchically. And so let's see this with a 2-bit adder. So suppose that I give you this 2-bit adder and I ask, can you derive an expression of the same form as this one, but with a generate term that covers both bits, both full adders, and a propagate signal that covers both full adders, right? And so it's G or P and C in. But what are these two terms? So can you write an expression that does this? Yes, we can, right? It's not. It's actually very straightforward. So we can start by just writing C1 as a function of C0, right? So C1 is G1 or P1 and C0, and then we expand C0. So G1 or P1 and, open parentheses, G0 or P0 and C in. And if you just distribute this P1 over the whole thing, you end up with G1 or P1 and G0 or P1 and P0 and C in. So can you tell me what G10 and P10 are? So G10 is just these two terms, and P10 is just these two terms, right? OK, so the point is that now we can compose this hierarchically. So if I give you a long, if I give you a long string of bits, let's say 32-bit operands, then we're going to follow the following strategy. First, we're going to generate and propagate signals for the individual bits. We're going to have this little green block here that produces a 2-bit output that's just the concatenation of G and P. I'm going to call this GP for brevity. Then we're going to have a tree of GP blocks that combine adjacent G and P signals. And so these two signals, the generate and propagate of the combination, are just the formula that we saw before, right? So if you have if you're trying to combine two sets of signals into one, well, if the upper part you generate, if the upper part generates, or the lower part generates and the upper part propagates, and you propagate if both parts propagate. This, despite the soup of indices, is actually a fairly intuitive formula. And finally, we need a block to compute the individual carries. So there are many ways that you can, many variants of carry look-ahead adders. We're going to see the Brent-Kang CLA, which is actually really simple. So as I said, our first step is to generate and combine all the generate and propagates by building a tree. So we first generate all the individual propagates, and then we group 2 by 2, right? So we produce, each of these is telling you how to skip 2 bits, right? So if I give you the carry of 5, you can generate the carry of 7 with GP76. You can keep going, and then again, build this tree. So with GP70, if I give you the carry in, you can produce the carry out directly. And this is a logarithmic depth, right? And so how does delay grow with the number of bits? Logarithmic. OK, so it's pretty easy to see that once you have this tree, you can obviously produce the carry out for GP70. You can also produce the carry out for everything that finishes in 0 here. And then for all the other carries, you can essentially add, take the carries that you already have and use them in the next stage with the generate and propagate signals from before. And so here is the full circuit that generates all the carries, again in logarithmic delay. So just to summarize, there are many different designs. You can see in the literature there are other designs that have more circuitry but less latency, like Cogistone. And then there are different variants for each type. This is not useful only for adders, but actually for any one-dimensional binary recurrence. And so you can turn any recurrence into log n time to take log n delay. And this will be useful, for example, to build fast comparison circuits. All right, that's it for today. See you on Thursday.